You've heard of quantum mechanics. You know it's weird, involves cats in boxes, makes physicists argue about reality. But here's what nobody tells you. The world's top physicists have been using quantum mechanics to build lasers, computer chips, and MRI machines for decades, and most of them will openly admit they have no idea what it actually means. Not just philosophically. They disagree about what the theory is fundamentally telling us about reality. Because while the math works incredibly well and the predictions are spot on, the picture it paints of the world is so bizarre that even Einstein spent much of his later career trying to prove it wrong. Let me start with what quantum mechanics isn't, because that's where most explanations go off the rails. It's not primarily about consciousness creating reality, though measurement is genuinely puzzling. It's not about parallel universes or mystical mind-matter connections. Quantum mechanics is a mathematical tool for predicting what happens when you poke very, very small things with instruments. But here's what makes it so unsettling. When you look at what those predictions actually say, they describe a world that works nothing like the world you experience every day. Think about flipping a coin. In your everyday experience, that coin is either heads or tails at every moment during its flight through the air. You just don't know which one until you catch it. Quantum mechanics describes something completely different. According to the theory, an electron, nature's version of that coin, doesn't have definite properties until you measure it. Now, what do I mean by doesn't have definite properties? I mean the electron literally doesn't have a specific location or a specific speed. It's not hiding these properties from you. They simply don't exist yet. The electron is in a kind of limbo state where all possibilities exist at once, waiting for measurement to make one of them real. This is what physicists call superposition, and it's nothing like your daily experience. Imagine a light switch that's genuinely both on and off at the same time. Not flickering between them, not broken, but actually existing in both states simultaneously until someone checks. That's closer to what quantum mechanics is telling us about particles. This isn't just about our knowledge or our limitations. According to quantum mechanics, particles are fundamentally different from anything in your daily experience. The theory says they genuinely lack definite properties before measurement. Now, quantum mechanics wasn't invented by someone sitting in a chair thinking deep thoughts about reality. It was discovered by physicists in the early 1900s who were trying to solve very specific, very practical problems, and they kept getting answers that made no sense. The first crack came in 1900 when Max Planck was figuring out why hot objects glow the colors they do. The math only worked if he assumed energy came in discrete chunks, packets he called quanta, instead of being smooth and continuous like everyone expected. Then Einstein showed that light itself comes in these packets, which we now call photons. Then other physicists found that electrons in atoms could only exist at specific energy levels, like they were climbing a staircase instead of a ramp. By the 1920s, the evidence was overwhelming. At the smallest scales, everything comes in discrete chunks. Energy, light, angular momentum, all quantized. But that was just the beginning of the strangeness. Here's where quantum mechanics reveals its truly alien nature. And I need you to stick with me because this is where even brilliant people's intuitions completely break down. Picture an electron, and you want to know where it is. In normal physics, this would be straightforward. The electron has a definite position at every moment. You just need a good enough measuring device to find it. Quantum mechanics says something that sounds insane. The electron doesn't have a definite position. Instead, it has what's called a wave function, a mathematical object that tells you the probability of finding the electron at different locations if you measure it. And here's the part that made Einstein uncomfortable for the rest of his life. According to the standard interpretation, this isn't just a limitation of your knowledge. The wave function is the most complete description possible of the electron's state. So what does this actually look like? Before you measure it, your electron exists as a cloud of possibilities. It's not secretly hiding at one location. It's genuinely spread out across all possible locations, with different probabilities for each spot. The moment your detector interacts with the electron, something extraordinary happens. All those possibilities suddenly collapse into one definite outcome. You find the electron at one specific location. But here's what's genuinely mind-bending. Quantum mechanics can tell you the probabilities for different outcomes with incredible precision, but it cannot tell you which specific outcome you'll get in any individual measurement. And this isn't like rolling dice, where you assume there are hidden factors determining the outcome. Quantum mechanics says the randomness is fundamental. There is no deeper level of reality determining which outcome occurs. You might think this is just a problem with our measuring devices. Maybe we're disturbing the system too much, or our instruments aren't sensitive enough. But the most famous experiment in physics proves this isn't a measurement problem. It's a feature of reality itself. The double-slit experiment sounds simple. Send electrons one at a time through two parallel slits and watch what happens on the screen behind. If electrons are particles, you'd expect two stripes on the screen, one behind each slit. But that's not what happens. The electrons create an interference pattern, alternating light and dark bands like waves would make. But here's where it gets weird. If you try to figure out which slit each electron went through by putting a detector at one of the slits, the interference pattern disappears. The electrons suddenly behave like normal particles again. This tells us something that should be impossible. The electron doesn't go through one slit or the other. It goes through both slits simultaneously, interfering with itself until the moment you try to measure which path it took. The act of measurement doesn't just reveal a pre-existing reality. It creates what that reality becomes. Now, if you think that's as weird as it gets, quantum mechanics has some surprises for you, because what I've described so far is just the warm-up act. Einstein called the next part spooky action at a distance, and he spent years trying to prove it was impossible. When two particles become entangled, which can happen when they interact or are created together, their quantum states become connected in a way that has no equivalent in normal physics. Picture this: you have two electrons that are entangled, so their spins are always opposite. Before you measure either electron, both exist in that same limbo state I described earlier. Each one is simultaneously spinning up and spinning down. But the moment you measure the first electron and find it spinning up, you instantly know the second electron will be found spinning down, even if it's on the other side of the galaxy. Now you might think this is just normal correlation, like having two coins that you know landed differently, but you don't know which is which until you look. But in 1964, a physicist named John Bell proved something remarkable. He showed mathematically that the correlations quantum mechanics predicts are stronger than anything normal physics allows. What Bell proved is that there's no way to explain these correlations using local hidden variables, the idea that each particle carries some hidden information that determines how it will behave when measured, and that particles can only influence each other when they're close together. The experiments have been done thousands of times since then, and Bell was right. The correlations are exactly as strong as quantum mechanics predicts. What this means should make your head spin. Measuring one particle instantaneously affects the state of its entangled partner, regardless of the distance between them. This doesn't allow faster-than-light communication. You can't use entanglement to send messages. But it does mean that quantum mechanics describes a fundamentally non-local reality. Space doesn't separate entangled particles the way it separates everything else. Then there's the question that keeps physicists awake at night. What exactly counts as a measurement? The standard interpretation of quantum mechanics essentially says, don't ask. The wave function collapses when a measurement occurs, but when does the collapse happen? Is it when the particle hits your detector? When the detector sends a signal to a computer? When you read the result? These questions don't have clear answers. Some physicists, like Hugh Everett, decided the wave function never actually collapses. Instead, every possible outcome of every measurement actually occurs, but in different branches of reality. This is the many worlds interpretation. Every time you measure that electron's position, the universe splits into multiple parallel universes, one for each possible outcome. In some branches, you find the electron here. In others, you find it there, and all branches are equally real. Other physicists couldn't accept that level of weirdness. David Bohm proposed that quantum mechanics is incomplete, that there are hidden variables we can't access that determine the outcomes of measurements. In Bohm's interpretation, particles do have definite positions and velocities at all times. but they're guided by a quantum potential that creates the appearance of randomness and non-locality. Here's what's remarkable. All of these interpretations make exactly the same predictions for any experiment you can actually perform. They're empirically indistinguishable. The math of quantum mechanics is crystal clear and incredibly successful, but what that math means about the nature of reality remains hotly debated nearly a century after the theory was developed. And this isn't just philosophical navel-gazing. As we build quantum computers and quantum communication systems, we need to understand not just how to manipulate quantum systems, but what we're actually manipulating. Are we creating superpositions of computational states? Are we splitting the universe? Are we accessing hidden variables? The answer affects how we design and optimize these technologies. There's also something called the quantum to classical transition that puzzles everyone. Quantum mechanics clearly applies to electrons, photons, and atoms. But what about larger objects? In principle, there's no size limit. The equations should apply to everything, but we never see big objects in superposition. Your cat is never simultaneously alive and dead, despite what Schrödinger's famous thought experiment suggests. The leading explanation is something called decoherence. Larger objects interact so strongly with their environment that their quantum superpositions are destroyed almost instantly. But exactly where and how this transition occurs is still being worked out, and it's one of the most active areas of research in physics today. So why should any of this matter to you? Because quantum mechanics isn't just an abstract theory about tiny particles. It's the foundation of the modern world, and it's about to reshape your life in ways you probably haven't considered. Every electronic device you own works because of quantum mechanics. The semiconductors in your phone and computer rely on quantum properties of electrons in silicon. The GPS in your car requires quantum corrections to atomic clocks. The MRI machine that might save your life uses quantum properties of hydrogen atoms in your body. Lasers, LED lights, solar panels, all quantum devices. But we're now entering what many scientists call the second quantum revolution. Instead of just using the bulk properties of quantum systems, we're learning to directly manipulate individual particles and their quantum states. Quantum computers are already being built by companies like IBM, Google, and dozens of startups. These machines will be able to solve certain problems exponentially faster than any normal computer. This includes breaking most current encryption systems, which means the security of everything from your bank account to national defense will need to be rebuilt from the ground up. But it also means solving problems in drug discovery, materials science, and artificial intelligence that are currently impossible. Quantum cryptography promises truly unbreakable communication, secured by the laws of physics themselves rather than mathematical complexity. If someone tries to eavesdrop on a quantum encrypted message, the act of measurement will disturb the quantum states and reveal the intrusion. Quantum sensors could detect gravitational waves, dark matter, or brain activity with unprecedented sensitivity. Quantum networks might connect quantum computers around the world, creating a global quantum internet. But here's the deeper point. Quantum mechanics is forcing us to confront fundamental questions about the nature of reality that go far beyond technology. What does it mean for something to exist? What's the relationship between consciousness and the physical world? How do we reconcile the deterministic evolution of the wave function with the apparent randomness of measurement outcomes? These aren't just philosophical puzzles, they're questions that will determine how we understand ourselves and our place in the universe. If quantum mechanics is correct, and the evidence suggests it is, then reality at its most fundamental level is probabilistic, non-local, and genuinely weird in ways that challenge our deepest intuitions about how the world works. This matters for how you think about causation, free will, the nature of time, and the relationship between mind and matter. It matters for how we design artificial intelligence systems and how we think about consciousness. It even matters for how we approach other scientific questions, from the origin of the universe to the nature of life itself. And here's something that might surprise you. You don't need to understand the math to grapple with these questions. The conceptual puzzles of quantum mechanics are accessible to anyone willing to think carefully about what the theory actually says about reality. In fact, some of the deepest insights have come from physicists who focused on the conceptual foundations, rather than just the mathematical formalism. So, quantum mechanics is a mathematical theory that makes incredibly precise predictions about the behavior of small particles. And those predictions describe a reality that's fundamentally different from anything in our everyday experience. Particles exist in superposition until measured. Measurements create reality rather than just revealing it. Entangled particles share correlations that transcend space and time, and the randomness isn't due to our ignorance, it's built into the fabric of reality itself. We've built our modern technological civilization on this theory without fully understanding what it means. We can manipulate quantum systems, build quantum devices, and make quantum predictions with extraordinary precision. But the question of what quantum mechanics tells us about the nature of reality remains as mysterious today as it was when Einstein and Bohr were debating it in the 1920s. That's not a failure of science, it's a reminder that reality is stranger and more wonderful than we ever imagined. And as we enter the age of quantum technologies, we're not just building better computers and communication systems. We're probing the deepest mysteries of existence itself, one quantum measurement at a time.